So this is going to be lecture 17. Just, like a sort of reassurance that, the last couple of lectures we were looking at PRGs for log space algorithms, or in general small space algorithms, and trying to see what we can say about them. This lecture will actually not deal with those at all. So even if some parts of the last couple of lectures where you haven't completely internalized, it should be completely okay for this. To me, this lecture is one of the, it's one of the first examples of putting together pseudorandom objects from in one context and then using them in a completely different context. So we'll be focusing on this, and in some sense, the focus of today is going to be to construct pseudorandom generators in some conditional sense, in the sense that if something else were true, or if certain other kinds of objects existed, then how do we construct PRGs of the types that we are interested in? And everything that I'm going to be presenting today is going to be a very influential paper by Noam, Nisan, and Wigderson. I think the paper is just titled Hardness versus Randomness or something. And it's, at least in my undergrad, I remember thinking that it was a very surprising result, in the sense that it sort of says that if something is hard, then something else is easy, which is a very counterintuitive sort of statement. It's like a flip that strangely happens, but in some sense, if you look at it from the context of a pseudorandom object sort of notion, hard functions happen to be pseudorandom objects. Pseudorandom generators happen to be pseudorandom objects. So in some sense, we shouldn't be too surprised that the existence of one kind of pseudorandom object seems to lead to the existence of some other kind of objects. Okay, that's going to be the agenda for today, and we'll slowly go into the details of it. But let's just do a recap, and in fact, mostly recap of whatever we'll need for this lecture. The rest of it is not going to be particularly important. Okay, and of course, we need the definition of what a pseudorandom generator is in general. And just to drive home the point, it's basically some map that maps a seed of length d to, and it somehow stretches it to something like length m. Such a thing is called an epsilon PRG for a class C. Typically, C is a class of some Boolean functions of a certain type, like maybe functions computable by size S circuits or something of that sort. Okay, and you sort of want to say that the expected behavior of any test in C under a uniform input versus a uniform output of a PRG, they should not differ by too much. So in some sense, if A is provided a string X, which either could be a completely uniform string, or maybe I picked a uniform seed and just applied G on it. As long as A is not able to tell these two apart, we will say that such a map is called a PRG. Okay, and this epsilon just refers to how much of a deviation between the ideal scenario and the PRG scenario you have. Okay, and ideally we would want D to be as small as possible, so that it stretches as many bits as possible. We would like G to be explicit, in the sense that computing G on a certain seed should not be ridiculously hard. So there should be some this thing, and normally this epsilon parameter is something that's usually a lot in your control. Like most of the time, typically what people do is they just choose epsilon to be, for example, if C is the class of size n squared circuits, they just choose epsilon to be 1 over n squared or something of that sort, or 1 over n power 5 or something. And just forget about the fact that there is this extra epsilon that is sticking around. But it's just an artifact of the definition. The definition needs an epsilon, but mostly this epsilon is not something that bothers you at all. Okay, and one of the things that we saw in about 3 lectures ago was that the supposed weaker notion of what is called a next bit unpredictability of a certain, or whatever, certain function, somehow it happens to be equivalent to PRGs if you're willing to trade a little on the parameters. Okay, just to recall, in case people don't immediately remember what next bit unpredictability is, it's just saying that I give you x1 through xi minus 1 in a certain sequence. So this x1 through xn is taken from some distribution. We will say this distribution is next bit unpredictable if there is no function, or there is no efficient algorithm that takes the first I minus 1 bits and somehow manages to predict the ith bit with some advantage. What do I mean by some advantage? That is, it manages to successfully predict the ith bit with probability half plus something. whatever that something is what is called the advantage. Okay, and if you can somehow do something non-trivially better than random guessing, then we will say that such a sequence is next bit predictable. And the knot of this is that, as long as there is no circuit and no I such that this happens, we will say such a thing is next bit unpredictable. Okay. Now, obviously, if something was next bit predictable, you have a distinguisher between the output of the generator and the output of the uniform distribution, which is just basically predict the next bit and see if it matches. Okay. But surprisingly, it also went the other way. That is, if it is a PRG, it actually is next bit unpredictable, and if it's next bit unpredictable, it is a PRG. And we saw Nisan's generator, but today Nisan's generator will just not be necessary for the lecture at all. But that was just one example of a generator where the seed length was something like log squared n for a certain natural class of algorithms. And we also saw that the ideal generator, in some sense, the benchmark that you should try to aim for should be something that looks like log s plus log 1 over epsilon, where s roughly refers to the complexity of the class you're interested in. That is, how many bits do I need to describe a certain function in my class? And turns out that seems to be the right thing to keep in mind. Okay. And we also mentioned that if we manage to find a PRG that has seed length that just looks like log s plus log 1 over epsilon, then notice that if s was polynomial and epsilon was also like inverse polynomial or something, this entire thing is just logarithmic. And therefore, you can afford to just run over all possible seeds and just de-randomize any arbitrary BPP algorithm by just, instead of running over the 2 power m random bits, you now run over the 2 power d random bits. And fortunately, 2 power d turns out to be polynomial in m, so therefore we are in good shape. So that would end up saying that basically for decision algorithms, randomness does not really give you any more power. It's basically polynomial. So this is just a rough recap of all that has happened, about PRGs. And so what I want to do today is to basically focus on something that I briefly mentioned earlier, which was to try and ask ourselves, suppose we wanted to build a PRG. How do we go about building something of that sort? Okay. So again, just to recap, what does it mean to say something is next bit predictable? This is exactly what I had said earlier, which is that there is some index I and an algorithm which comes from the class that says it's next bit predictable by this class, such that this A happens to predict the ith bit given the prefix x1 through xi minus 1 with some significant advantage, where the significant is whatever is above half. This epsilon is what refers to what this advantage is. Okay. And so this is something that we saw in lecture 13, which is that saying that you want an PRG versus saying that you want the output of the PRG to be next bit unpredictable is roughly the same if you're willing to ignore some minor changes in the parameters, in question. Okay, there's some mild changes that will keep happening, but it's not really a big deal. Okay, so today we are going to just focus on how the hell do we build PRGs. Okay, so we're going to start with a toy case, slowly improve it a little by little, and then come up with a way in which we can come up with a substantial improvement as long as we change our our mindset a little. Okay, so this is something that I had mentioned last time, but I'll just go over this, which is that let's just focus on getting a stretch of 1. That is, I want to build a generator generator G that takes d bits and is supposed to output d plus 1 bits. And again, instead of PRGs, we might as well assume that I just want to build something such that the output of the generator is next bit unpredictable. Now the question is, how do we go about doing something of this sort? Now, since we already have d random bits, let's just tell ourselves that the first d random bits is just x1 through xd. I just need to fill up one more random bit somehow. Okay. In the one more random bit, let's just say it is some function g of x1 through xd. or some G 0, 1 to the D 2, 0. Okay, and let's ask ourselves, what do we want from G? Like, for what sort of G's will this actually be a next bit unpredictable function or a next bit unpredictable output or what? Okay, now notice that for next bit unpredictability, I need to somehow argue about if I give, I don't know, a prefix of this output to any efficient algorithm, it shouldn't be able to predict the next bit. Now, notice that if I just give you x1, I mean, predicting x2 is impossible because x2 is a truly random. It has no correlation with x1. Similarly, if I give you x1 and x2, predicting x3 is impossible. So certainly, if at all there is a next bit predictor, it's not going to happen for any of the prefixes here. The only prefix that sort of makes sense is this prefix, because the next bit is actually a function of the previous bits. And it's just a question of, can we do that efficiently? Okay. So let's just take the definition of next bit predictability. Like, when will this not be a generator? If it so happens that there is an algorithm A, okay, such that A, when provided x1 through xd, equals g of x1 through xd with probability something like half plus epsilon. Well, if that happens, then certainly this is next bit predictable. So for it to be next bit unpredictable, g just needs to be a function such that this does not happen. So that is, so we want to say that this this g must be hard to guess for any sizes circuit. I mean, I'm assuming we are building a PRG for sizes circuits, otherwise this will change. What do I mean by this? That is, I want to say for all A in the class of interest, probability that g of x equals A of x is at most half plus epsilon, where the probability is over x. Okay, so that's what it means to say hard to guess. I will use a parameter epsilon hard to guess to just keep track of the fact that this is the sort of advantage I'm working with. Okay, so what this basically tells you is that when, I mean, this is just a, I mean, like a way of saying that if I feed it a, what is that? Like if I feed it a randomly chosen x, I want g of x to not just be computable, I don't even want it to be guessable. Okay, that is, you can't really do much better than random guessing. Okay, if we somehow manage to find a suitable function g that has this magical property, we automatically have a generator that happens to stretch by 1 bit. Okay, so this basically says that, you know, if we find a hard function g, then we have a generator that can, we have a PRG that stretches by 1 bit. So firstly, therefore, the task now boils down to finding out this hard function, because once we find a hard function, we have a generator, but it stretches by 1 bit. Okay, so 1 bit is not anything like, you know, to celebrate in a situation of this sort. So we would want something more. Okay, but let's say somebody has provided us such a hard function g. There is a function g which is super hard to even approximate. Okay, now okay, we built one stretch of 1 bit. Can we stretch by more bits? So here is a slightly different argument. I mean, so this is basically the same version where you now think of your input as having dk bits as opposed to d bits. And now I'm going to stretch by k additional bits. And it's the most natural thing you will think of, which is think of your dk bits as actually a sequence of k d-length inputs. Okay, and again, I'll just output whatever was the seed that was provided to you, just output that. And now apply g on the first input, g on the second input, blah, 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 till g on the kth. Okay, and it's a very simple argument to basically tell you that the same method, whatever we did above, will now also tell you that that G1 through, I mean, the output of this new generator is also next bit unpredictable. Basically the same thing. The only thing is a question of, given a prefix of these things, can you predict the next and just convince yourself that this ought to work? Okay. But I mean, even if it does work, I mean, it still stretches by just k bits. And it still may, in the sense that, if you look at the relative stretch that you're getting, you started off with something like dk bits and you're outputting dk plus k bits. Which means the relative stretch is something like, what is it? It's like d plus 1 over d, which was the same even earlier. So we're not doing anything special in this, whatever, in a supposedly a slightly better argument or something. And the problem is, I mean, like, this seems to run into this following question, following issue, which is that as long as you want G to be acting on disjoint subsets of the seed bits, which is what we were doing. We said that let's take these dk bits, let's split them into k disjoint sets of size b and apply G on each of them. Well, as long as if that's what you're doing, then notice that the output length by input length will never be larger than d plus 1 over d. Just because of the fact that you can't pack that many disjoint subsets into whatever this seed thing. I mean, if you want disjoint subsets of size d, well, there are only k of them. And if that's all you're going to, that's all the extra bits that you're going to generate, then you will basically generate only k more bits. Okay. And this is the reason why none of these arguments seem to be yielding much. And so here is a key idea, which is, let's just look at this and say, why do we want disjoint subsets? Okay. And the main idea is going to be, what if the subsets were almost disjoint? Okay, by which I mean is that what we'll do is we'll take our input sequence, try to find a bunch of subsets that are not quite disjoint, but they have some very minor overlap, and somehow output the G, the hard function evaluated on each of them. And the hope is that this should still look random. They're being very wishy-washy here, but this is the rough intuition as to why we're doing this. And the main advantage of doing this is that roughly we seem to think that it might be easier to pack a lot of almost disjoint subsets into a small universe rather than disjoint subsets into a small universe. Because the number of sets you pack seem to be related to how many new bits you end up generating. So that's the reason why we are doing this particular thing. And we are going to explore this idea. This was in some sense the key insight in Nisan and Wigderson's paper, which is to just take the above stupid argument or a stupid generator to generate k bits and just say, okay, why are we dealing with disjoint subsets? Why not make these subsets almost disjoint? Okay, so are there any questions so far? Is the general outline clear as to what we are trying to do? Okay, so now what I'm going to do is I'm going to focus on what do we mean by almost disjoint? Because these sort of objects are very well studied in mathematics, and we will focus on basically the only thing that we'll need here, and you will have an opportunity to do more of this in the next problem set. Okay, and these sort of almost disjoint subsets are often given a name. It's what are called combinatorial designs. Okay, and here is the abstraction, which is that we will say some collection of subsets, say S1 through Sm, which all belong to a universe of size d. Okay, this d is going to be the seed length eventually. Okay, I mean, here it was dk, and in the universe of size dk, we had picked up k truly disjoint subsets. So similarly, here in the universe of size d, we're going to pick up sets S1 through Sm, which are almost disjoint. And we will formalize that and say that such a thing is called an L, A design if they satisfy the following two properties. So firstly, the size of each Si must be exactly equal to L. because in some sense I'm going to think of G as being a function on L bits. So that, I mean, G works on L bit function. So that's what this L is supposed to be. Okay. And the second property is probably the more important property, which is that this is the almost disjointness here, which is that I want whenever I not equal to J, that is you take two different subsets, their intersection must be small. So this again, A is a parameter. Typically A will be much smaller than L. So something like L by 100 or L by 1000 or something of that sort. And this is what we want. We want to build a lot of subsets. Ideally, we want M to be as large as possible within a smallish universe. Hopefully D is not too large, and such that I have a lot of subsets that all have the same size, which is some size L or something, but somehow their pairwise intersection is quite small. How do I get rid of this thing? Okay. How do I get rid of this damn thing? Does anyone have any clue? Okay. Okay, good. Okay, so this is the goal. So our notion of almost disjoint subsets are basically going to be what we have written here called combinatorial designs. Okay, so let me give you a rough, I mean, like an example of such a design. These are not going to be the best sort of parameters, but it's very instructive. So, so think of your universe as basically being, I don't know, let's say your plane. Okay, okay, R2, or if you want, you think of a finite field and think of a plane there or something. And let's say each SI is basically a line in the plane. So these are all my, this is S1, this is S2, this is S3, this is S4, etc. Okay, now in the sort of domain that you're interested in, you might be able to say that, okay, there are lots of lines that are inside a certain plane. Maybe you have a certain count of that. That's what M is. And each line has a certain number of points. So that's what L is. And thankfully, we know that two lines intersect at most 1 point. And therefore, A is at most. I mean, A is like 2. So that SI intersect SJ is strictly less than 2, which is 1. Okay, this is an example. It's just a question of whether the parameters are good enough for something. I mean, I wrote R, so everything here was infinite. But you can imagine doing this in some sort of finite domain. Okay, but so this is roughly what these designs look like. Okay, so okay, let's keep this in mind. But so we just came up with some definitions. So obviously, we would want to know, do such designs exist? Can we find a suitably large number of subsets in some universe that happen to be pairwise disjoint? Sorry, almost pairwise disjoint. Okay. Okay. So hopefully by this time you have seen this sort of argument enough that it should push you into first trying whenever you are encounter a question of this sort. I mean, you should often try to just say, okay, let's just try to pick these sets at random and ask, well, what is the chances that, I mean, like, you know, such a random choice will succeed? This is what we are going to do. Like every set, I'm just going to pick an L size subset of a universe D at random. I'm going to keep on doing this. And I'm going to ask, what is the first point when I now have a small intersection? So I'm just going to do a really silly thing. So let's pick the sets at random. Okay. Now let's assume that we have already picked some sets S1 through ST. Okay. These are all belonging to this universe D. Okay. Now ST plus 1 is a random subset of size N, because I mean all the sets of my design are expected to have the size N. So let's just pick up a random set of size N. Okay, and now let's ask ourselves, what is the probability that ST plus 1 intersect SI is less than less than A for all I that we have chosen so far. Where the probability now is only over ST plus 1. Actually, let me just remove this T plus 1 so that the S without any subscript is the random variable that we have right now. These S1 through ST, etc., have already been chosen. So this is what I want to get a sense of this happening. What's the probability that this happens for all subsets? Okay. So if this happens, if this event happens, we will say that S is a valid extension. By this I mean that we had a subset of things S1 through ST. Now I can add S to this collection. That's what we are saying, and we are asking, if we keep choosing sets at random, what's the probability that we always remain in a valid extension? Okay, it's often easier to analyze the other direction, which is the probability that S is not valid. This is basically equal to the probability that there exists an I such that S intersect SI is unfortunately at least A. That is, it happens to have a large intersection with something that we have chosen already.
Do you want to quantify this with T?
The thing is, like this also has a subscript, this also has a subscript, etc. So
No. This S is not valid. This probability depends on T, no?
Oh,
how
sorry,
many?
yeah. Not valid at whatever, at the T plus 1th step.
Yeah.
Okay. So when you're looking at the T plus first step, the probability that it is not valid is that, it intersects with, there exists I in this collection T, such that S intersects with one of the chosen sets a bit too much. Okay. Now this, I can write it as, this is at most T times probability that S intersects. Maybe let me not do this. So basically what we are going to do is we are going to just ask ourselves, let's fix one of the sets, let's say S1 or S2 or whatever, and ask, what is the probability that this happens? Because the probability that it happens for any of these I's is going to just be the sum of the probabilities. So what I just want to focus on is fix a set, some SI, which has already been chosen. Now S is chosen randomly, and ask, what is the probability that this happens? So the probability that S intersect SI is at least A for a fixed SI. Okay. So what can you say about this probability? What sort of upper bound can we give for this? And we just want some reasonable upper bound. Okay, so here is one way of doing this. So this is my set SI, and it is in this universe of size B. So if I want to choose a set S that has a large intersection with it, well, let's do one thing. Let's first choose the intersection. This is the intersection of size A. Okay. So how many ways are there of choosing that intersection? Well, there are L choose A many ways of choosing that intersection. And the remaining, whatever, L minus A elements, I can't quite say it has to lie here, because that would mean that the intersection size is exactly A. But let's just, we just want an upper bound. So let's just put D choose L minus A. To mean, I don't care if the remaining L minus A things you pick from wherever. If you again end up picking from here, well, that just means that your intersection is more. Or if you end up picking from here, your intersection is more, but I don't care. Okay, there's a lot of overcounting happening here, but I don't care. It's just an upper bound. Okay, these are the number of good, number of sets that happen to satisfy this event, and I need to, of course, divide this by D choose set, because these are the total number of possibilities of choosing an L size subset among a D size subset. Are things okay so far? Okay, so I suspect things are fine. So let's just try and get a better sense of what the hell this is. Okay, so I'm going to write D choose L minus A divided by D choose L. Okay, because I mean, let's just write down some binomial coefficients and see which all cancel, which all survive, etc. etc. So this is just going to be, what is this going to be? The denominator is going to look like D factorial by L factorial into D minus L factorial. And the numerator is going to have another D factorial by L minus A factorial into D minus L plus A factorial. Okay, a bunch of things cancel off. And you are left with something that looks like L factorial by L minus A factorial. And this is going to be D minus L factorial by D minus L plus A factorial. Okay, so I'm going to do a weird thing, which is multiply by A factorial and divide by A factorial, because this clearly looks like some L choose A sort of term, which was just missing this. So I added that. Similarly, this also looks like something choose A sort of term. So which is why I added this. This is nothing but L choose A divided by, what is this going to be? D minus L plus A choose D minus L, or D minus L plus A choose A. Okay, and since we are always interested in the, what do you call it? This A is always smaller than L. Notice that D minus L is certainly smaller. Sorry, this guy is like smaller than D. So one, no, sorry, it's smaller than D. So therefore, I mean, maybe I'm missing something. Okay, I'm going to write this because I think I possibly made a mistake here. But I'm going to work with this mistake. If not, there is some minor adjustments that one needs to do, which I'm just going to ignore right now. This is going to be L choose A divided by D choose A. This is probably wrong, is it? It's maybe going the other way. I'm not entirely
I think
sure.
you're right, because this D choose A is exceeding D minus L plus A choose A, right? Because I think so, because D is greater than.
Yeah, but I'm dividing by more, therefore.
Dividing by more, that's a problem.
Okay, so then clearly I messed up this calculation. But I mean, but I do know the following fact is true. So therefore, let me just write that something off here. But I mean, morally speaking, there's not anything too much. I mean, it's just a question of L. I mean, maybe I need to put something a little smaller than D choose A here. If I put D by 2 choose A, maybe it's okay. I don't know. So something like that. So morally, this is fine.
You can
so
just put D minus L choose here, no?
Yeah, I can put D minus L choose. Yeah, that's right. That's right. Yeah. So I can certainly put D minus L choose. So what does this say? This basically says that the probability that S intersect Si is at least A. This is at most L choose A the whole squared by D minus L choose A. Okay. So this implies that the probability that there exists an I such that S intersect Si is at least A is at most this T times L choose A the whole squared by D minus L choose A. Okay. So this basically says that, okay, so this should have been D minus L because of my error in calculation. Okay, this basically says that as long as this quantity is still something much smaller than 1, it says that there is a valid extension, because the probability of this is like strictly smaller than 1. So it says you can certainly extend it by 1 more, and you just keep repeating. So this basically says as long as t is at most this quantity that we have, this probability turns out to be smaller than 1, and therefore there is a good choice for st plus 1 to continue. And we will get stuck only if this t happens to be larger than, the inverse of this. Okay, so this is a way of arguing that there exist designs that have number of sets being something like d choose a divided by l choose a the whole square. Again, there is the d minus l nonsense, which I messed up. Okay.
That's
This
square is
There
wrong.
won't be any square.
I got it a square there. Yeah, okay. So it's like roughly d choose a divided by l choose a the whole square, if we ignore that l on top. Okay. So, but anyway, let's put some numbers to get a sense of what has happened here. Okay. And this is just something that I calculated yesterday. This is probably a wrong calculation because of this L thing. So what I'm going to do is I'm going to choose L to be equal to something like 10 log n. Okay. And A to be equal to log n. And D to be equal to something like 1000 log n. That is, what's happening is we are picking up sets in a universe of size 1000 log n. Every such set is of size 10 log n, with some property that if I pick two different sets, they intersect at most log n intervals. Okay, and if you work out the parameters, so this d choose a roughly turns out to be something like n power 11.4, and l choose a works out to be something like n power 4.6. So this implies that we have, n power 11.4 by n power 4.6 squared, and it turns out we have at least n squared sets. Okay, so we have there are combinatorial designs that have about n squared sets in them. So just to compare, notice that the universe is of size just order log n. And we have managed to pack exponentially many sets in this universe that happen to have some like small pairwise intersection sort of property, which is very, very different from the situation we had earlier when we were asking for completely disjoint sets. If you want completely disjoint sets, you really can't do much. You can't pack too many sets there. But the moment you weaken things a little bit, you sort of say, okay, I can afford a small intersection as long as the intersection size is smaller than the set size. You can somehow pack a lot more elements into this set. Yeah, Abhishek, you had a question?
Yeah. So this problem, I think it also can be interpreted as finding almost orthogonal vectors in some space, because
Yes,
if I dot product the characteristic functions.
Great question. So you might be robbing me of some problem set things, but you're absolutely right. Like right now, in some sense, this is something to tell us that there are designs, but we should not be satisfied with them. We should be asking, okay, like we found some designs, but the question is, can we find explicit constructions? Okay, yeah. And the answer to this is yes, and you will find this in problem set 3. Okay, and there, I don't know if I'll be using the orthogonal vector sort of idea that you had in mind, but in some sense, like it will be. I think that at least the idea, at least the construction I have in mind, has a lot of flavors very similar to what you're asking for. But yeah, hold that thought. In problem set 3, you will see a really, really explicit construction, which is a sort of algebraic in nature, which I think is like and there is a very general way of constructing these designs from other kinds of pseudorandom objects called codes. Because we are really just asking for things to not intersect too much. It has a very coding theory sort of flavor. And now turns out you can convert it, as long as you have a decent code, you can convert it to a combinatorial design. So yeah, so I just want to mention that this is very different from asking for disjoint sets. Because if you wanted disjoint sets, you will not be able to find more than d by L of them. Like that's the largest number of disjoint sets of size L in a d-sized universe. But now, surprisingly, you can find exponentially many sets that are almost disjoint. Okay, so I mean, is this argument to sort of roughly say that there are exponentially many sets, or I mean, at least the whatever this random argument, is that clear to people? Okay. By the way, if you are more comfortable dealing with binomial coefficients in general, there is a very simple way of just using Stirling's approximation to get a sense of how large is this, etc. And you can just prove the following simple general statement, which is going to be enough for today's lecture, which is that if you are interested in finding 2 power a sets, which is often the case because we'll be interested in finding some n sets or something, so a will often be log of that. Okay, so if you want to find some m sets where m equals 2 power a, and as long as you have this L to be bigger than a in some decent sense, I mean, if L is bigger than 2a or something, it turns out it is sufficient to pick a universe of size something like 2L squared over a. Okay, you just need to plug this into these expressions, estimate these binomial coefficients, and convince yourself that, I mean, that's going to be larger than 2 power a or something. I mean, this quantity is like bigger than 2 power a. But this is the sort of general statement that we will be using. And in fact, there are explicit constructions that do the same thing. I mean, you don't need to do this in a random fashion. Okay, so we'll just tell ourselves that if the goal was to find lots of sets where the lots refers to just 2 power a, and you have a choice of the size of the sets in mind, which is this L parameter, then the universe size is roughly 2L squared over. That's all you need.
By the way, if you depend, the explicit constructions which you plan to give in the homework will be very explicit. But your construction is already, the probabilistic construction already is reasonably explicit, no?
I mean, right now we are using randomness in the process.
No. But how many sets are there? There are at most
good. Okay. Yeah. Right. I mean, like we can just fix one such construction and just be done. By the way, there is also, in fact, in Salil's notes, he actually shows that this is a construction you can use one of your old techniques of conditional expectation to actually de-randomize this construction. You don't really need to use fresh randomness all the time. You can just use the conditional expectation method to just remove all randomness. So
you don't even need conditional. You don't even need conditional, no? The number of sets is n power 1000. You pick a first set, then just go over all of them, find out if the next set satisfies this. Then go over the next set. It's n power 1000 into n squared.
That also you can do. Okay.
So
for this regime of parameters, I think that's already good enough.
Yeah, possibly L square by A, you can't do that.
Yeah, so if you want a more general, I mean, if you can't afford something like going over all possible sets of this size, then maybe you need one of those de-randomized constructions. Yeah, but in the problem set, we will see a really, really explicit construction of such a design. Okay, so far we basically said that we started off with the goal of trying to come up with PRGs, and we came up with a really stupid PRG, which was just applying a certain hard function on disjoint sets of inputs. But then we said that this is not going to give us too much of stretch. So one way to get a lot of stretch was to basically not do disjoint inputs, but instead do sort of almost disjoint inputs. And now we have formalized the notion of what almost disjoint means. So now what do we want to do? Now we need to sort of now define what is the generator. Okay. And the rest of the time that I have, I'm just going to try and convince you that this generator is a great generator, that this actually works. Okay, so I'm going to change notation a little bit. I was using G for the hard to guess function. I'm going to start using H because when I'm saying it, when I say G with respect to G, etc., it just sound weird. So I'll use H for hard. Okay, so let's assume that somebody has provided us a hard to guess function. Okay, it's a function on L bits. It takes L bits and returns some 0, 1. And we are assuming that it's very, very hard to guess the output of this function. Okay. And here is a candidate generator. Earlier, we also gave Z1 through ZD, but we are going to get enough stretch that this D is going to be so much smaller. So let's just not worry about those. So here is a generator. It's going to stretch D bits to M bits, where M is the number of sets in your collection. Now notice that was exponentially more than what you started off with, for the right range of parameters. And you just do the following. You take Z1 through ZD. S1 is one of the sets in your collection of size L. So just look at Z restricted to those coordinates in S1. So that is some L length string. Apply H on that. And similarly, restrict on S2. That is some other L length string. Apply H on that, etc., etc. And the last bit is going to be, look at the restriction of these Z1 through ZD on SM and apply H on that. Now, each of this is going to be 1 bit. I have M such bits. So therefore, the output is an M bit string. Okay, so is the definition of the generator clear? Okay, so I hope things are fine. So therefore, this is a candidate generator given a design S1 through SM. So once you specify a design, this is giving you a generator, and we'll just assume that such designs always exist. We just said that they exist. We'll also be able to find one efficiently. So that's what we're going to be using to build such a generator. Okay, and what we want to say is, as long as H was suitably hard to guess, this G is going to be an amazing PRG. Okay. So I'm going to write the theorem in more like the contrapositive version, because that's how we'll end up proving it. So this is the main theorem of Nisan and Wigderson that said the following, which is that suppose this was not a PRG. What does that mean? It means that there is some circuit C of small size that happens to predict the output of G. Then we will show that given such a circuit, I can add a few more bells and whistles on top of it to come up with a circuit that actually approximates this supposed hard function H pretty well. Okay. And in a way such that, the size of the circuit C prime is going to be whatever was the size of C, and I will just add M times 2 power A many additional gates. So the size just increases by S plus M times 2 power A, which is why we wanted A to be small. That is the pairwise intersection property. We want that to be small. So we're basically saying, give me a next bit predictor for the output of G, and I will give you a function. I'll give you a circuit that approximates H well. So if you flip this around, this basically says, if you believe that H is something that is very, very hard to guess, then you should believe that there is no such next bit predictor. And since the output of G, if it is not next bit predictable, then we know that it is going to be a PRG. There's some loss in parameters, which I'm just not going to worry too much about. Okay, so the content of the statement is basically that if H was hard enough, then G is indeed a PRG.
So for this sentence to make sense, M into 2 power A must be smaller than 2 power L. Otherwise, because you always know there's a function circuit of size 2 power L that.
Yeah, that is true. So in fact, just to make sense, what is the stupid circuit for H? H is some function on L bits. So there is always going to be a stupid circuit of size 2 power L for this. Just imagine writing a big, the circuit just has a big table. For every string, it just tells you this is the output, this is the output, this is the output, etc., etc. And you can certainly just look up and do that. I mean, there are plenty of ways to see this, and this will make sense. Makes sense when something like s plus m times 2 power a, this will turn out to be like not just less than or equal to, it'll turn out to be way smaller than 2 power n. That's most
your choice.
Sorry?
And I think your choice of parameters already has this property.
Yeah. But that was just one example choice. But often what will happen is when you instantiate this theorem, somebody will give you a hard H. And depending on how hard H is, you might set up various other parameters. We'll see an example, we'll see a couple of examples of that. And that time it will be clear. But no matter what we do, it will always be the case that m times 2 power a is going to be way smaller than 2 power a. Okay. Good. So let's just, before we go into the proof of this theorem, I just want to show you one example instantiation for this. Okay. So we were assuming that, like whatever, somebody provided us this family of functions that was epsilon hard to guess for a certain size. Okay. Now let's just instantiate one such, dream scenario and see what this would mean. Okay. Let's just say that it is epsilon hard to guess for circuits of size, I don't know, let's say 2 power r by 100. Okay. Like we just said, there are circuits of size 2 power r that completely compute this function. But let's assume that, if your circuits are of size 2 power r by 100, it's very hard to even guess the function. Like you can't even do much better than random guessing. Okay. Suppose that was the, someone gave you such a function. Now, what are you going to do with it? Okay. Now, here is what we are going to do. I'm going to instantiate the Nisan-Wigderson generator that we just saw from 0, 1 to the D to 0, 1 to the M. Okay. With the following parameters. As usual, A is always going to be equal to log M, because that's the number of bits that you need. I mean, you need 2 power M sets. So we will use whatever was this explicit construction that we had, and we'll choose D to be equal to roughly this. It's just a question of what should L be. Okay. And let me just say L equals, just work this out. So this is going to be, I'm going to choose L to be equal to 100 log of M cubed. And I will soon explain why I came up with this number, 100 log of M cubed. Okay. And notice that the above thing basically says that D is also going to be some constant times log M. Because D was like what, L squared over A or something. So L squared is some constant times log squared M divided by something times log M, divided by log M. So you'll get some constant times log. Some ugly constant, I don't care. I don't know, 90,000 or something. Okay. So this is going to be the setup. And now I need to use a hard function on L bits. So I'm given a family for all R. I will choose it for and use H equal to HL inside the NW generator. Okay. Okay. And now I claim that this particular generator is actually a PRG for size M circuits. Okay. So, so the claim is that G is a PRG for size M circuits. Or let me just say G is epsilon next bit unpredictable for size M circuits. Okay, so suppose not. So suppose it was not next bit predictable. What does the above theorem say? Now I have a size m circuit that apparently epsilon next bit predicts G, because that's what I'm assuming, suppose not. And the above theorem basically says, oh, in that case, you will be able to construct a different circuit that actually whatever approximates or guesses H, okay, of size at most S plus M times 2 power A. So this implies that there is a circuit C prime that epsilon whatever guesses H with, what can I say about the size of C prime? This is at most whatever was the size of the original circuit C, which I assumed is a size M circuit, plus I need to add this extra factor of M times 2 power A. Okay, now notice that this 2 power A was also equal to M. I'm just going to be liberal and say that this is at most M cubed, because it's like M plus M squared or something. I'm just going to say it's M cubed. Okay. Now, what does the hardness of H tell you? It says that in order for you to approximate HL, okay, so, but HL needs circuits, okay, I'm running out of space here. So let's just do a calculation here. So, so L was equal to something like 100 log of M cube. But in order to compute HL, I'm saying that I need circuits of size at least 2 power L over 100. Okay, which means that HL needs 2 power L over 100 size to guess. And we just set it up such that 2 power L over 100 is something that turns out to be M cube. And I mean, we just started off by saying that, so I shouldn't probably have put a strictly less than here. We started off with the hardness assumption that says that in order for us to guess H correctly, we need size at least 2 power L over 100, which was like M cube. But I just gave you a circuit of C prime that has size significantly smaller than M cube that happens to do this guessing. And that's a contradiction. Okay, so this tells us that the generator that we defined above is actually an epsilon next bit unpredictable sort of generator. And since PRGs and next bit unpredictabilities are the same, then we have a PRG as well. Okay, so let's just get a sense of how good or bad is this? Is this as a generator? What's the seed length eventually? The seed length is just going to be some, I don't know, some constant times log n. So this is just order log n. Okay, and how much time does GY take? In order to compute GY, I need to compute H. Where is this? Where is the generator? I need to compute H on each of these whatever sub inputs. Okay, let's just assume that computing the design is actually super easy. We will see an explicit construction in the problem set. So the design is given to us. So it's just a question of computing H on each of these M inputs. So this is going to be M times whatever the time taken to compute H. Okay, and so it makes sense to sort of say that H is something that can be if H is provided to you as a truth table, then H is something that can be computed in M times 2 power L time. Okay, which turns out to be poly. So computing the generator takes only poly M time. You only have log M seeds. I mean, the seed length is just order log M. So now any randomized algorithm that you have, which if you think it can be done in a circuit of size M, you can now instead just brute force over all the seeds you have right now. Just run over all possible log M seeds, compute the generator on each such seed, feed that to your randomized algorithm, then now figure out, do you accept at least 2/3 plus epsilon, or 2/3 minus epsilon, or less than 1/3 plus epsilon. Okay, so all of this together will tell you that BPP is equal to P. Okay, just to emphasize, if we have a hard to guess function. So it says that, if somebody provided to you a function which is super hard to guess, okay, then you actually come up with a generator which is like this dream generator that has only order log m. The seed length is just order log m, and somehow, the generator just works. Okay, and it basically tells you that for all decision problems, randomness is not really giving you any more power than polynomial. So BPP just happens to be equal to P. It's a remarkable theorem. And in fact, if you play around with the proof, all I did was that I set it up such that the hardness was equal to something like m cube or something. And if you can actually do this depending on what sort of hardness you have versus what sort of consequence you end up getting. Okay, so we were doing 2 power omega r because we were saying that the hardness was something like 2 power r over 100. So that was what led to this particular set of parameters. But you can imagine, suppose someone told you that, no, I only know hardness that looks like 2 power root r or something. Okay, then if you work things out, you will turn out that D will turn out to be polylog of M. So the running time of your complete de-randomization will turn out to be 2 power polylog. But on the other hand, let's say someone just tells you that it's only hard to approximate for super polynomial, some super polynomial hardness that you have. That is, it's bigger than r power a constant for any constant. Then you will get a slightly weaker de-randomization. You will get that, it's what is called sub-exponential. So this class is called sub-exp. So this will tell you that, it sort of gives you a way of saying that if somebody gave you a hard function, then you can get some de-randomization. The quality of de-randomization depends on how hard your function is. Okay, and this is what we meant by the flip that you have, which is that saying that the existence of hard things is somehow saying that randomness is in some sense easy. Saying that you can get rid of randomness. Anything that you could do with randomness, you could do without. Okay, for decision problems. Yeah. Okay, so I hope with the above theorem, which is the Nisan-Wigderson theorem, which we haven't proved, which I'll prove in the next about 10 minutes or something. That's going to be, that will tell us that, presence of hard to guess functions immediately give you some sort of de-randomization of BPP. And the harder the function is, the better your de-randomization is. Okay, so are there any questions so far? Okay, cool. So let's proceed with the proof of the theorem. So I'm just going to write down the theorem in a slightly smaller font, which is that somebody gave us a predictor for the generator, and we want to use that to come up with an approximator for, or rather a guesser for the inner hard function H. Okay. So let's just write down what do we know. So say C is a next bit predictor. Okay, C is the circuit of sizes that supposedly predicts the next bit. What does this mean? This means that then by definition, there exists some I from 1 through M such that C, when provided the prefix, somehow manages to tell you what the next bit is. Okay, so let's just write that down. What do we mean by that? So what is C provided? C is given H of Z given S1, Z restricted to S1, blah, 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 till H of Z restricted to Si minus 1. So it takes the value of H on each of these other subsets and somehow magically happens to guess this Z given to Si with significant probability, where the randomness now is again over the choice of Z. Okay, so I hope it's clear that, when this is just the definition of saying that we have a next bit predictor for the above generator. Okay, now, okay, how do we go about doing this? So now, basically, this starts to look like some circuit is managing to compute H or managing to guess H. It's already in the sort of form that seems to, that we want. Except that this stupid thing is not, there are parts of this that are present in each of these other bits, other coordinates. That seems to be the slight problem here. But nevertheless, let's say these are my, okay, let me use blue for the other thing. So this is Z conditioned on S1, sorry, not condition, Z restricted to S2, blah, 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 till there is Z restricted to Si, there is Z restricted to Si minus 1, and then there's a bunch of things afterwards, which I don't care. Okay, now I'm going to think of all of these guys, okay, as my string Y. Because I eventually want to I want to think of this above expression as something that computes H of Y. Okay, now let's call all the Y strings as these blue strings. These are not blue. I'll use a blue color just for this. Now I need to give the circuit these things. And at the face of it, it feels like that already requires a computation by H. But we are somehow trying to say that, we can build a small circuit for this. Okay. So now the point is, because of the pairwise intersection property, some of these blue coordinates will actually be sprinkled. There could be some weird intersection that in each of these sets. Because some of these coordinates might share the blue things, because I don't know. I'm not told that Si minus 1 is disjoint from Si. I'm only told that the intersection is at most A. So each of these has at most A blue coordinates. That's what I have been told. So let's just write the above statement. So I'm going to take this star and write this as, let's look at the probability over non-blue Z of probability over the blue Z of C of H is Z given S1, H of Z given Si minus 1. This equals H of Y, because H of Y is basically all the blue coordinates. I should have probably put expectation everywhere. So maybe let me just replace this with an expectation.
Well, the second one is still a probability, no?
Sorry,
unless you put an
second,
indicator event.
Yeah. So second one is a probability. So this, I'm told, is at least half plus epsilon. Okay. And we'll now do the most standard thing. If the expectation of a certain random variable is at least half plus epsilon, then it better be the case that there is some choice of this random variable that makes sure that it takes value at least half plus epsilon. Okay, which implies there is some way to freeze non-blue Z's such that the following holds, which is that the probability of, this is only over the blue things anymore, C of H of Z given S1, H of, Z, saying given restricted to Si minus 1, this equals H of Y This is at least half plus epsilon. But the randomness is, I mean, I've just fixed the z's that are outside of these blue region. Okay, are things clear so far? Okay, and now comes the key observation. Okay, z given si, okay, only has at most a blue z's. That's because of the pairwise intersection property. Each of these things, what has happened right now is that most of the variables in them have already been frozen to certain values. The only variables that have not been frozen are those that happen to be blue in color, because they somehow happen to have an intersection with y. Everything else has been frozen, which means this h of z given s1, after you freeze all the non-blue things, is really just a function that depends on a bits. Because those are the only a bits that you currently don't know, because everything else has been fixed to some specific value. Okay, so this implies.
I got confused here. Can you repeat this?
So yeah, so earlier what was happening here? So let's focus on. So let's say this was z conditioned on s1, and we were applying a certain function h on it, and that was what was being fed to the circuit, the guesser circuit C. Okay, but we eventually realized that, look, these were the only blue coordinates that that was there here. Okay, now all other coordinates which we have basically we have managed to fix them to some 0, 1, 0, 0, 0, 1, 0 something. Okay, so I need to figure out, I am given a certain y. I need to know what do I need to feed into my circuit C. Earlier, I was supposed to feed into the circuit C the z given s1, which just seems to be too hard for me, because computing h on that seems to be too hard. But now really, what do I need to do? I mean, once I fix a y, I now know what the blue coordinates are. So I need to apply some Boolean function on the blue coordinates so that it matches this h. Right? So whatever is the output of this, so since only blue coordinates are unfrozen, okay, this map from y going to h of z given s1 is a function on just a coordinates of y.
Yeah, so I'm getting confused because you've written z restricted to si. Maybe you want s1 up to si minus 1.
No, so I want to focus on each one of them. I'm just focusing on just this. Just the first coordinate alone. And I'm saying the first coordinate alone is some Boolean function that depends on just a bits of y. Right. Okay. Similarly, the second coordinate will also be some Boolean function that depends on a bits of y. Yeah. Etc. Etc. That's what I want to feed into this guesser circuits. Okay. So what we are just going to say that, which means that this is computable by a stupid circuit of size 2 power 8. And by this, I just mean just this one bit that was being fed into, just the first bit that was being fed into the guesser circuit. Okay, so now let's just draw the picture of what really do I want. So this was the guesser circuit, and it needed this is supposed to be h of z restricted to s1, and this is h of z restricted to si minus 1. Okay, that was my circuit C. But I'm trying to build a circuit that takes these blue coordinates y, and whose goal is to somehow approximate h of y. Okay, so here's what I'm going to do. Now, this says that the first coordinate I need to feed in is some Boolean function of some A of them. So I'm just going to build some circuit of size 2 power A for this. So the second coordinate will also be some Boolean function on some A of them. So therefore I'll build another circuit of size 2 power A. And similarly, the last guy might be another thing of length 2 power A. So I'll do this. Now this entire thing, this is what I'm going to call my circuit C prime. Okay, so C prime takes as input some blue coordinates, decides what it needs to feed in to each of these, to the inputs of this guesser circuit, and just runs the guesser circuit. Okay, and notice that the size of this is at most whatever was the size of C, which was S, plus 2 power A times, I don't know how many ever coordinates it needed to begin with. I mean, the largest it can be is like M. So it's at most 2 power A times. And basically that completes the proof.
Yeah, okay, makes sense. Yes.
Yeah, so this is, I mean, it's just using the fact that, yes, H on an L bit input, it might be hard. But once I freeze, I mean, everything outside of these blue coordinates, most of the inputs here were frozen anyway. So it really just depends on A inputs. And therefore, we are just building a stupid circuit of size 2 power A to compute whatever was that Boolean function. Okay. And yeah, and that completes the proof. It also tells why we wanted this A to be small, because this A was capturing how much each of these slivers, like how large are these slivers. And yeah, that more or less completes the proof. Just to reiterate what we managed to show, we basically said that if you have a circuit of size S that happens to predict the output of the Nisan-Wigderson generator, then you actually have a circuit of not much larger size. I mean, we just needed to add some bells and whistles to it, such that that happens to approximate the function H. Okay, and so this together combined with everything will basically give us a way of saying that if you have a certain amount of hardness, then you can get a certain amount of, you can get some consequences this way. So the presence of hard functions, or rather an explicit construction of a hard function, gives you an explicit construction of a PRG. And the harder the function, the better your PRGs. Yeah, was there a question? Okay, so so in the remaining about maybe 5 minutes or something like that, I just want to tell you a bit about what else has happened. And we will do more of this exposition in the next lecture, where I won't be going into the proofs of it because it's involved and there are components of this which you have not seen, because it uses these things called codes. But at least I'll try to give you a motivation for this, because it really is like a major success of pseudorandomness, in the sense that it puts together various things which are all pseudorandom objects on its own to come up with a connection between one pseudorandom object and another pseudorandom object. So it's a pretty cool sort of thing. So let me just start off by saying a few, just the theorem that I would like to at least tell you about in the next lecture, and give a rough sketch of how one goes about doing this. This is really amazing theorem of Impagliazzo and Wigderson. Okay. That basically says that you can actually get PRGs from worst case hardness. Okay. So in fact, I'm going to be very vague and just write. Okay, I'll just try to impress upon you the statement of the theorem, or the rough content of the theorem, and we will see this in a bit more detail in the next lecture. We won't be seeing the full proof of this. We'll only see the main ideas that go into the proof of this. So here, what did we want? for Nisan-Wigderson, okay, we want a hard to guess function h from 0, 1 to the L to 0, 1. Okay, and this was saying that if so the definition was for all whatever, let's say circuit C, the probability that C of x equals h of x, this should be at most half plus epsilon. That is, you shouldn't even be able to do anything better than random guessing. Okay, so in such a thing is called an average case hardness. That is, when x is chosen on average, okay, the circuit is going to make a mistake very, very often. Okay, but that's not the same thing as saying it's worst case hard. So here is a definition of worst case hard. If I can spell correctly. Which is just saying that any small circuit C will make a mistake on some x. That is, there exists an x such that C of x is not equal to h of x. I mean, a hardness with respect to a certain size. So any circuit of that size will make a mistake on some input. Now notice that the above statement is saying that any circuit of small size will make a mistake on nearly 49% of the inputs. Okay, and here all we are asking for is like, there's no circuit that will get h right correctly everywhere. Okay, it's just that all I'm asking for is that there exists, I mean, any small circuit computing this function will make a mistake somewhere. And the main sort of result of Impagliazzo and Wigderson was a way of going from this assumption to this assumption. That is, they roughly said, you give me a function that is just worst case hard, in the sense that no circuit can get it right everywhere. I will take that function, massage it a little bit, and come up with a new function, h prime in this case, such that it is actually average case hard. And once you have that, you can plug it into the Nisan-Wigderson thing, and you can get the same sort of consequences that you do from starting from just worst case hardness. Okay, and in the next lecture, what we will do is we will try and break it up into building blocks. I won't prove any of the building blocks, but I will tell you the various building blocks that go into taking a function that is hard on the worst case and slowly making it harder and harder, so that you eventually reach this point and you can just plug it into Nisan and Wigderson. And there'll be a lot of cool ideas that go into the process of going to this transformation of a worst case hardness to average case hardness, which are interesting in its own right. And if we had seen more of codes and so on, we may have been able to actually give the full proof of it. But that is something, since we didn't do it in this, this version of the course, like going into the proof is perhaps not going to be useful right now. But Salil Badan's manuscript on pseudorandomness has a complete proof of this. In fact, much of the chapter on pseudorandom generators deals with the complete proof of this theorem. So for those who are interested, you can just go over the manuscript as well. So in the next class, I'll just write this down. Okay, it's just going to be an exposition, but this is going to be without proofs of the AW theory. And depending on how much time we have, I'll also tell you a bit more about some related results and that will, I mean, I think next class will be the last class on pseudorandom generators, and then we'll move on to the next module on what are called extractors, unless I mean, I'll think about more to see what else I want to present that is within whatever we have done so far, so that we don't have to introduce drastically new ideas to give the other expositions and so on. Okay, so let me stop here unless there are some questions. Okay, so if there are no further questions, then at some point we'll put up a poll on Academy. Let me just take the stream offline. Okay, I'll put up a poll on